Hello, Chem1A. This is Chapter 11, Lecture Video 7, and we're going to be talking about hybridized orbitals. So, in the last lecture video, we talked about how atomic orbitals overlap to form bonds. In reality, though, that simple model really only works for pretty simple molecules, typically diatomics. As soon as you get to a triatomic or polyatomic molecule, it really stops working. For instance, if we consider a relatively simple structure like methane, which is CH4, a tetrahedral, it just has these 4 bonds around it, no lone pairs, pretty as simple as it gets as far as simplicity. It doesn't work with overlapping atomic orbitals. We know that the bond angle here for methane is 109.5 degrees. But the problem is, if we're overlapping atomic orbitals, the orbitals you're going to have to use to do that as far as atomic orbitals are going to be the p orbitals and the s orbitals. And none of the p orbitals have an angle to one another of 109.5 degrees. See, these orbitals here are different by 90 degrees. And the same with these two are different by 90 degrees, which is distinctly different from 109.5. And we've measured the bond angle of methane. It is 109.5 degrees. So there is obviously something going on here that we're not taking into account. So another issue with this is that carbon, if you look at its orbital energy diagram, has in the 1s orbital 2 paired electrons, in the 2s orbital 2 paired electrons, and in the 2p orbital only 2 electrons unpaired. Typically the number of bonds that you can form is equal to the number of unpaired electrons you have. Well, carbon only has 2 unpaired electrons here. This is very different from what we know carbon does. We know carbon always forms pretty much 4 bonds. So what's going on here? There's more to this issue.
What's happening is orbitals can mix or hybridize, as we call them, to form new, what we call valence bond orbitals. This is a really rare way of saying it. The most common way is just saying hybrid orbitals. These two are interchangeable, and this is by far the more common. So let's look at the electron orbital energy diagram for carbon. We're just going to look at the valence shell. Technically, you have a 1s here, and it's full. If you want to look at the full electron orbital diagram, electron orbital energy diagram. But if we just look at the valence electrons, because remember, valence electrons are the ones responsible for bonding, we have a couple issues here. We only have 2 unpaired electrons. As I said earlier, valence bond theory predicts that we have to have unpaired electrons participating in bonding, which means since I only have 2 here, I should technically in carbon only be able to form 2 bonds. But we know methane, CH4, exists and that it has 4 bonds around carbon. Also, when we were talking about how to draw organic molecules, one of the comments we always said is carbon almost always forms 4 bonds around it. Well, that's not what this shows. So what's going on here? These guys are going to mix together to form what we call hybrid orbitals. Now, there are 5 different types of hybrid orbitals that we're going to talk about in this chapter. The first one is called sp3 hybrid orbital. So if I mix this orbital, this orbital, this orbital, and this orbital together, I can form 4 new orbitals. They're all going to be at the same energy. So notice that because I mixed this 2s orbital with these 3 2p orbitals, the energy resulted somewhere in between the 2 orbitals, right? They're the 3 or 4 orbitals, right? These 3 orbitals are at higher energy, this one's at lower energy, so the end hybrid orbitals are kind of in between. They average out a little bit. Because they're all at the same energy, when we put our 4 valence electrons in them according to Hund's rule, we got to fill them one at a time. These new orbitals are what we call sp3 hybrid orbitals. Why sp3? Because we mixed one s orbital, so the s, and 1, 2, 3 p orbitals. So that's why we have the superscript 3 there. These hybrid orbitals actually do have bond angles that match 109.5 degrees like we see in methane. And more importantly, if we think about the hydrogen coming in, each hydrogen has a 1s orbital because that's where its one unpaired electron is, and they're going to overlap with these guys each, all 4 of them, to form our methane compound. So again, we're filling each one of these one at a time due to Hund's rule that we learned about in chapter 7. So let's talk about sp3 hybridization, kind of a summary. How do we figure out what type of hybrid orbital is present? It's actually based on the electron pair or group geometry, not the molecular geometry. I can't stress that enough. It's based on the electron group geometry. sp3 hybrid orbitals are always present around a central atom that has an electron group geometry of tetrahedral. More importantly, when we combined atomic orbitals to make hybrid orbitals, however many orbitals that we're mixing together to get the hybrid orbitals, that's how many hybrid orbitals are going to be formed. So in sp3, we mixed one s with 3 p's. This got mixed me 4 orbitals is what I'm mixing together. I got 4 sp3 hybrid orbitals when I did that because of that. And this 4, if we remember how many groups of electrons are around a tetrahedral, is also 4. There's no coincidence there. That's by design. And so that's an intro into hybridization. We'll continue talking about the other types of hybrid orbitals. We don't just have sp3. There's also sp, sp2, sp3d, sp3d2. There's a bunch of different hybrid orbitals, and they are all due to the mixing of different atomic orbitals together. But that'll end this lecture. If you guys have any questions, as always, please email me or come to my office hours.